Based on the mathematical definition of the rate distortion function, we have shown that like the differential entropy for a Gaussian source, the rate distortion function for a Gaussian source also has the distinction of being larger than the rate distortion function for any other source with continuous distribution and the same variance. Now, this is a very important result because for many sources it can be very difficult to calculate the rate distortion functions, and in such situations it is helpful to have an upper bound for the rate distortion function. Now, it will be very useful if we could also find the lower bound for the rate distortion function. Shannon in his 1948 paper has described these lower bounds and appropriately called Shannon's lower bound. The reference is C. E. Shannon, A Mathematical Theory of Communication, Bell System Technical Journal, volume 27. There were 2 parts and published in 1948. We will state the lower bound here without derivation. If one is interested in detailed derivation, then it could be referred to this reference. T. Berger, Rate Distortion Theory, A Mathematical Basis for Data Compression, published by Prentice Hall in 1971. So, the Shannon's lower bound for a random variable x and the magnitude error criterion, that is d x y equal to mod of the difference between x and y, is given by Shannon lower bound is equal to differential entropy minus log of 2 E d, where d denotes the specified distortion level. Now, if we use the squared error criterion, then the Shannon's lower bound is given by differential entropy minus half log 2 pi E d. So, this result is for squared error criterion, that is dxy is equal to x minus y squared. So, to summarize, we have provided a mathematical definition for the rate distortion function and also calculated the same for 2 important sources, one binary source and the other was a Gaussian source. We have also obtained the upper bound and lower bounds for any arbitrary independent identically distributed source. Now, these functions and results are specially useful when we want to know if it is possible to design compression schemes to provide the specified rate and distortion for a given source. These results are also useful in determining the amount of performance improvement that we could obtain by designing better compression schemes. Therefore, the rate distortion function plays the same role for lossy compression scheme that entropy plays for lossless compression. Now, in the last class we had discussed two approaches to calculate the rate distortion function for a source. One approach which we utilized to calculate the rate distortion function for the binary source and the Gaussian source was to calculate the lower bound for the average mutual information and then show that this bound is achievable. The other approach is based on a computational approach. Now, we will not go into the detailed derivation of this approach, but we will present the salient features of this approach. The algorithm by itself is very simple. Now, in order to do that, we will use simplified notations as follows. Conditional probabilities, that is probability of yj given xi by a matrix Q, where we assume that the source alphabet is of size n, that is there are n elements, and reconstruction alphabet is of size m. So, in this case Q matrix by definition is given by probability of y1 given x1, probability of y2 given x1 to probability of ym given x1, probability of y1 given x2, probability of y2 given x2, probability of ym given x2, and finally, the last row is probability of y1 given xn, probability of y2 given xn, and the last term is probability of ym given xn. Now, using this notation, we can write the average distortion for a given source and specified distortion measure as a function of the matrix Q as follows. Distortion D, which we have seen, is basically function of conditional probabilities, can be rewritten as D function of Q. And similarly, the average mutual information, which is again function of conditional probabilities, can be written as function of the matrix Q. Now, we introduce the set Q D, which consists of the matrices Q of the conditional probabilities for which distortion as a function of Q is less than or equal to some specified distortion level D. That is, Q D is equal to set of matrices Q which satisfy the distortion criterion. Now, to recollect the mathematical definition for the rate distortion function, R D is equal to minimum of I x y. This minimum is over conditional probabilities belonging to the set, where this set is equal to set of conditional probabilities such that distortion criterion is satisfied. So, based on our new notation, we can write the rate distortion function as R D is equal to minimum of I Q, where Q belongs to the set Q D. Now, based on this new notation, let us solve some few examples in order to understand these concepts in a much better manner. So, let us assume that we have a source alphabet of size n equal to 2 and reconstruction alphabet of size 3, that is m is equal to 3, and let us assume that the probabilities of the source symbols, that is p of x 1 equal to p of x 2 is equal to half. Let us specify the distortions between a source symbol and a reconstruction symbol in the form of a distortion matrix given by this is by definition T x 1 y 1 d x 1 y 2 d x 1 y 3 d x 2 y 1 d x 2 y 2 and finally d x 2 y 3, and this let us assume to be given as 0 1 3 3 1 0. What this distortion matrix means, that there is no distortion if source symbol x 1 is encoded into symbol y 1 and x 2 is encoded into y 3, otherwise there is distortion. And let us assume that the average permissible symbol distortion be less than or equal to d equal to 0.5. Now, let the two conditional probability matrices Q1 and Q2 be given as follows. Point 7, 0.2, 0.1, 0.1, 0.2, 0.7 and Q2 is equal to 0.8, 0.1, 0.1, 0.1, 0.1, 0.8. So, the sum of the row elements is always equal to 1. Now, for both these matrices, we may confirm whether or not they give an average symbol distortion satisfying the given constraint, that is d of q is less than or equal to d. This is what we want to verify. So, we find d q 1 as follows: double summation I is equal to 1 to 2, j is equal to 1 to 3, probability of x I, conditional probability of y j given x I, and the distortion measure between x I and y j. Now, let us plug in the values which have been provided. This is equal to half multiplied by 0.2 multiplied by 1 plus half multiplied by 0.1 into 3 plus half multiplied by 0.1 into 3 plus half into 0.2 multiplied by 1. Other two terms are 0 because dx1 y1 is equal to 0 and dx2 y, and this can be simplified as 0.1 plus 0.15, 0.15 plus 0.1 is equal to 0.5. Now, this clearly shows that d of q1 is not less than the specified distortion level, that is d equal to 0.5. Now, let us similarly calculate the distortion for the given matrix Q2. If we plug in the values similarly to what we have done here, then we can show that d of Q2 is equal to half multiplied by 0.1 multiplied by 1 plus half multiplied by 0.1 multiplied by 3 plus half multiplied by 0.1 into 3 plus half into 0.1 multiplied by 1, and this is equal to 0.4. Clearly, dq2 satisfies the constraint. Therefore, the matrix Q 2 belongs to Q D as opposed to Q 1, which does not belong to Q D. Now, we can calculate the average mutual information for all those matrices which belong to Q D and select the lowest one of this. Now, for the given example, we have only one matrix, that is Q 2, which belongs to the set Q D. So, let us calculate I of Q 2. For I Q calculation, we use the following relationship. Probability of xi, probability of yj given xi, log of probability yj given xi divided by probability of yj. And we also know that probability of yj is equal to summation of over I equal to 1 to 2 of probability yj given xi multiplied by probability of xi. So, we calculate I q 2 for q 2 since it belongs to q d, and probability of y equal to 1 from the given values can be evaluated as follows: probability of y equal to 2 is equal to 0.1 and probability of y equal to 3 is equal to 0.9 by 2 is equal to 0.45. And if we use this results and plug in for the relationship of I q 2, we get the following result. Plus half into 1/10 into log of 1/10 by 1/10 plus half to 1/10 to log of 1/10 divided by 0.545, and this on simplification is equal to 0.44706. So, having solved this example, now let us proceed and try to look in general what are the properties of the rate distortion function. So, we will investigate the properties of the rate distortion function. We will assume that we have a discrete memoryless information source, and let us assume that the source has n different symbols. Now, first let us see how does the rate distortion curve proceed as a function of the distortion level d. Now, we can show based on what we derive for the binary source and the Gaussian source that in general the rate distortion function has the following shape. So, it is a monotonically decreasing function with increasing d. The range of function is given by R d is greater than or equal to 0 and is less than or equal to the entropy of a discrete memoryless source. Now, this result can be shown as follows. We know that equivocation, that is h of x given y, is always greater than or equal to 0 and it is always less than or equal to the entropy of the variable x. And we also know, based on our previous study, that h of x is greater than or equal to 0 and less than or equal to log of n, based on the assumption that we have a discrete memoryless information source with the source alphabet of size n. Now, average mutual information is equal to h x minus h of x given y. Therefore, using the previous results, it implies that I x y is greater than or equal to 0, is less than or equal to h x is less than or equal to log n. Now, since the rate distortion function, that is R d, is the minimum of the average mutual information, that is I x y, we have rate distortion function less than or equal to average mutual information, and based on the previous results we can say, so R d is greater than or equal to 0 and less than or equal to h x. Next, let us determine the permissible distortion d may take on. So, the next property of the rate distortion function is to find the permissible distortion d. So, we know that average distortion dq is defined as double summation over I j of the quantity p x I probability of y j given x I distortion measure between x I y j. This quantity is less than or equal to the specified distortion level d. So, the smallest possible average distortion d minimum is obtained if for each source symbol, that is x I, we seek the reconstructed symbol y j, where d x I y j is minimum, and subsequently set this conditional probability, that is y j given x I is equal to 1, and thus set the remaining conditional probabilities of the reconstructed symbol given that particular source symbol xi equal to 0. So, let us define di to be minimum of dxi yj over I. Hence, d minimum is equal to summation of pxi d I is equal to 1 to n. Now, without loss of generality, we will assume that d minimum is equal to 0. If this is not the case, we modify the distortion d xi yj in such a manner that d minimum becomes equal to 0 again. This means that for every source symbol xi, there must be a symbol yj such that dxi yj is equal to 0. Now, since for the conditional probabilities we have yj given xi equal to 1, if xi and yj correspond to each other, that is distortion measure between xi and yj is equal to 0 is equal to 0, otherwise the equation will be equal to 0, so that I q is equal to h x. Now, q no longer appears here, so that it also directly follows that R 0 is equal to I q is equal to h x. So, in order to achieve 0 distortion, all of the information of the source must therefore be constructed at the destination. Now, let us determine the maximum possible average distortion. So, we are interested in finding out d max, and this can be determined as follows. Now, it can be shown that the rate distortion function is monotone decreasing for increasing distortion d. So, the maximum d then occurs for minimal R d, that is R d equal to 0. This means that the destination receives no information from the source. Let us denote the smallest possible distortion that is then still possible by d max. This value is achieved by constantly choosing that value yj for which the average distortion between an arbitrary source symbol and the symbol yj in question is smallest, and every other choice would lead to a larger average distortion. Now, the mutual information IQ is equal to Pxi probability of Yj given Xi log of probability Yj given Xi over probability of Yj. So, if IQ is equal to 0, then probability of Yj given Xi is equal to probability of Yj. So, if we choose conditional probabilities is equal to probability of Yj, which means that occurrence of Xi does not have any effect on the reconstruction of Yj, so that no information is reproduced. In that case, the average distortion dq becomes so the minimum value of dq is obtained by setting probability Yj equal to 1 for that value of j for which this quantity is smallest. So, this gives d max equal to minimum over j of the quantity P xi d xi Yj summed over I. Let us try to appreciate this result with the help of an example. Let us consider again the earlier example, but now we want to find d minimum and d maximum and the corresponding values of the rate distortion function. So, going back to the earlier example which we had discussed in the starting of the class, we can show that d minimum is equal to 0 and it appears if the matrix Q is of the form 1 0 0 0 0 1, where the distortion matrix was given as follows 0 1 3 3 1 0 and probability of x 1 equal to probability of x 2 was specified to be half. Now, this corresponds to R 0 equal to I q is equal to h x is equal to, based on this, 1. So, the minimum value is equal to 0 and the rate for the minimum distortion is equal to the entropy of the source, that is given by 1. Now, let us evaluate the maximum value of the distortion. So, d max is equal to minimum over j of the quantity P xi d xi y j summed over 1 to 2 is equal to Pxi is equal to half, therefore, is equal to half times minimum over j of d x1 yj plus d x2 yj, and this is equal to half based on this matrix times minimum of 0 plus 3, 1 plus 1, 3 plus 0. So, the minimum is 2 is equal to half times 2 is equal to 1. So, for this d max is equal to 1, the corresponding value of R d satisfies the relationship given here, and the corresponding conditional probability matrix Q is given as shown here 0, 1, 0, 0, 1, 0. In order to get a better and more clearer understanding of rate distortion function, let us solve another problem. The problem is given as follows. Given a binary source which generates symbols u0 and u1 from the alphabet u, the source symbols occur with the probabilities probability of u0 equal to p and probability of u1 equal to 1 minus p, where p is greater than 0 and less than equal to half. The Z channel for this is given as well. V0 and V1 are the destination symbols from the alphabet V. The transition probabilities, that is probability of Vj given Ui, are also given as follows. Probability of V0 given U0 is equal to 1 and probability of V1 given U1 is equal to 1 minus Q. We have been also provided the distortion between source and reproducing symbols, that is distortion between Ui and Vj is given as follows. Distortion between U0 and V0 is equal to distortion between U1 and V1 is equal to 0, and distortion between U1 V0 is equal to distortion between U0 V1 equal to 1. The Z channel is given as shown here. U0 and U1 are the input symbols, V0 and V1 are output symbols. Given this, we are required to calculate the average distortion dq, where q is the conditional probability matrix, and the solution is as follows. First, let us calculate the joint probabilities, that is probability of Ui and Vj. We calculate this as follows. Probability of U0 V0 is equal to conditional probability, that is probability of V0 given U0 multiplied by probability of U0, and based on the information provided, this is equal to P. Similarly, we can calculate the joint probabilities P U0 V1, which comes out to be 0, probability of U1 V0 is equal to Q into 1 minus P, probability of U1 V1 is equal to 1 minus Q multiplied by 1 minus P. Given this joint probabilities, we can plug this along with the distortions given between the source and reproducing symbols, and the average distortion becomes as follows: dq given by this formula is equal to q multiplied by 1 minus p. Next, we are required to provide the definition of the rate distortion function. Then for this problem, what is the maximal value of Rd? For what value of Q is this value obtained? And in this case, how large is the average distortion dq? The solution to this task, the solution for the same is as follows. For the rate distortion function, it is the case that Rd is defined as minimum of Iq. This minimum is over Q belonging to Qd, where Iq is the mutual information and Qd is the set of all conditional probability matrix such that distortion for that conditional probability matrix is less than or equal to the specified distortion level d. So, this is the definition of the rate distortion function which we had seen earlier. Now, we have also seen that the rate distortion function is maximally equal to HU, and this maxima occurs if there is a 1-to-1 relation between source and reproducing symbols. So, concerning the transition probabilities, this implies that we should have probability of V naught given U naught is equal to probability of V1 given U1 equal to 1, which implies that 1 minus Q is equal to 1, which implies Q is equal to 0, and now in this case the average distortion becomes equal to 0. Next question is, what is the minimal value of rate distortion function? For what value of Q is this value obtained, and how large is the average distortion dq in this case? Now, the minimal value of the mutual information Iq is equal to 0. This we have proved earlier, and thus the minimal value of the rate distortion function also equals 0. This minimum appears if the reproducing symbols give no information about the original source symbols, and this is the case if both symbols U0 and U1 give rise to the same reproducing symbol. So, in this case it leads to Q equal to 1 and now distortion is equal to 1 minus p. And the final question is, let us sketch rate distortion function as a function of d, and the solution to this is as follows. We have seen the maximum value is HU, minimum value is 0, and that is achieved for d equal to 1 minus p, and in between this it will be monotonically decreasing function. So, for d equal to 1 minus p, R d is equal to 0. There are two ways to calculate the rate distortion function. We have looked at one approach, which is to calculate the mutual information and find the lower bound for this mutual information and then show that this lower bound is achievable. The other approach is a computational approach. In the next class, we will discuss the computational approach to calculate the rate distortion function and also explore the application of the same to a binary case.